Have you ever stopped to think about your own memory? I mean, how on earth does your brain sift through everything you see and do all day and decide what's actually important enough to keep? It's a massive challenge, not just for us humans, but for artificial intelligence too.
Well, it turns out that robots trying to learn from their experiences run into this exact same wall. How can a machine build a useful memory without getting totally bogged down by every little detail? Today, we're diving into some really cool research that found an answer by looking at something we all do every night: sleep. So here's the setup. Researchers gave a robot a pretty simple task. Learn that a moving yellow flashlight always shows up right after a stationary red tool case. The real question wasn't if it could learn this, but what's the fastest, most efficient way for the robot to search its memory and make that connection?
Okay, so let's break down the first two ideas they tried, because they seem pretty logical on the surface. The first strategy is to just search everything. Every time the robot plows through its entire memory log to find a match. The second strategy is to search what's recent, assuming that the most relevant memories just happened. Both make sense, right? But as it turns out, both have a major flaw.
Yeah, that search everything strategy, it just doesn't scale. You can see it clear as day on this chart. As the robot's memory grows, the search time just goes up and up in a straight line. By the time it has 600 memories, it takes 6 seconds. In the real world, that's an eternity. That robot would be impossibly slow. Now, the search recent strategy is a bit more clever, but look at how erratic it is. For event 4, it's super fast, under half a second, because it got lucky and found a match right away. But then, for event 5, no luck. It had to dig deeper, and the search time just skyrocketed back up to 4 seconds. It's fast sometimes, but you can't rely on it at all. So if those two common sense approaches don't cut it, what does? Well, this is where things get really fascinating. This brings us to the breakthrough idea. A third strategy where you let the robot sleep. It takes an offline period not to gather new info, but to process and organize the memories it already has. So what do we actually mean by robot sleep? Well, it's a post hoc process, which is just a fancy way of saying it happens after the events have already been recorded. The robot basically disconnects from the outside world to sort through what it already knows, with no new data coming in to distract it. It's purely dedicated time for memory consolidation. And during this sleep state, the robot does 3 really important things. First, it prunes. Think of it like cleaning house. It throws out all the redundant, useless details. Second, it abstracts. It takes a ton of raw data, like pixel counts, and boils it down to a simple idea like, that's a big red object. And third, and this is the big one, it cues. It creates direct links between events that it now knows are related. So I really want to hammer this point home. Pruning and abstracting are great for efficiency, but cueing is the absolute secret sauce. This is the step that lets the robot build lightning-fast connections between what just happened and what it expects to happen next. So let's take a closer look at how this cueing actually works, because it's a really clever and kind of counterintuitive idea. It's all about making powerful connections between the boring parts of an experience and the exciting, novel parts. The key, the real secret, is to use the moments when it seems like nothing is happening. You know, when the robot's camera is just pointed at that stationary red tool case. Those seemingly boring periods are actually the most valuable part. Because those boring moments become the trigger. They become the cue for the important, novel events, like when that yellow flashlight suddenly appears and starts moving. The end of a static, boring moment becomes a giant signpost that says, hey, pay attention, something interesting is about to happen. So here's a little peek at the robot's memory before it goes to sleep. It's just a raw list of episodes. It's tracking things like pixel counts for different colors and whether there's movement. It's just a long, messy, and unprocessed list of data. And this is the transformation. Look what happens after sleep. Those jumbled episodes have been organized into one clean dream event. And check out the pointer column. The robot has created a direct link, a cue, from the memory of the static red object to the memory of the moving yellow one. It doesn't have to search anymore. It just follows the link. It's brilliant.
Okay, so the theory is sound. It all makes sense. But does it actually work? Let's look at the results.
Oh yeah, it works. After that offline sleep and cueing process, the time it took the robot to retrieve the memory was just over 0.2 of a second. That is a massive, massive improvement over the multiple seconds we saw with the other strategies. And what's crucial here is that the performance is consistently fast. This chart shows that across all these different events, the retrieval time is rock solid, right around 200 milliseconds. No more of those crazy spikes or slowdowns. Now, the robot can reliably and quickly anticipate what's coming next. So this is about way more than just a clever trick for one robot. This whole concept of offline memory processing, it has huge implications for how we can build more efficient, more capable artificial intelligence in the future. And the next step is to make this process even smarter. Right now, the robot identifies important events based on a simple cue, movement. The future goal is to give it a novelty algorithm, which would let the robot figure out on its own what is truly new and significant, making its learning that much more sophisticated. And this brings us right back to the beginning. What's so amazing about this research is that it's not just some abstract engineering solution. It actually mirrors what happens in biology. It provides a computational reason why sleep is so vital for memory in most mammals, including us. It's nature's time-tested strategy for learning from the past to predict the future. It's an incredible insight, both for building smarter machines and maybe for understanding ourselves a little better. Which leaves us with one final big thought. If this is how robots are beginning to learn, what will they be capable of once they've had a little more time to sleep on it?